I hope I am audible to everybody, and the screen is visible to everybody. So, I welcome all of you to the fifth live session of the course Thermodynamics of IIT Delhi. Uh, I am Abhigdev, a PhD scholar in the Department of Mechanical Engineering at IIT Bangalore, and I shall be a TA for this course, dealing with the problems related to the concepts that were discussed in the um, previous week theory class of the course, so as to help you with the problem solving skills and clear the doubts. Uh, I hope that um, uh, this live session these live sessions are beneficial to you, and I request all of you to join them, so as to make this outreach a success. And today, in today's session, we shall be discussing on the problems related to the properties of pure substances. So without further delay, let us begin with today's session. If at any point there is any doubt, please do ask. The first problem is a mass of 200 gram of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascal. Determine the volume change and the amount of energy transferred to the water. So, uh, what is happening in this? 200 gram of saturated liquid water. Let me draw the PV diagram of the process, pressure specific volume diagram. So, if we do this, then from saturated liquid point, say this is the saturated liquid point, it is completely vaporized, that it becomes saturated vapor point. Okay, so this is 1 and this is 2. This happens at 100 kilopascal pressure. 100 kilopascal. Okay, determine the volume change in this process and the amount of energy transferred to the water. Okay, so this is basically the saturation pressure, to corresponding to the saturation pressure of 100 kilopascal. The specific volume of the liquid phase is 0.001043 meter cube per kg, and specific volume of the gas phase is 1.6941 meter cube per kg. Okay, so what is the VFG value? That is the change in volume, specific volume from the liquid to the gas phase, is Vg minus Vf. So this is basically 1.6930 meter cube per kg. Therefore, what is the change in the volume? The volume change that is, let me denote it as delta V, is equal to the mass that is in the mass of the liquid water which is changing the phase, multiplied by the change in the specific volume. So this is 200 grams, so this is 0.2 kg multiplied by 1.69630. So this comes out to be 0.3386 meter cube per kg, and the amount of energy transferred to the water. So we basically have this relation for the enthalpy. We have enthalpy is U plus P specific volume. Okay, so the change in enthalpy, okay, from 1 to 2, okay, and that is the change in enthalpy from 1 to 2 is HFG at the saturation pressure of 100 kPa. Okay, so we can write HFG, this is the change in enthalpy from 1 to 2, is the saturation pressure, this will be UFG plus P saturation to VFG. UFG is equal to UG minus UF. So this is 2505.6 minus 417.40. These are the internal energy and at the of the gas phase and the of the vapor phase and the liquid phase corresponding to a saturation pressure of 100 kPa. So this equals to 2088.2 kilojoule per kg. Okay. So HFG can be written as this 2088.2 plus saturation pressure of 100 kPa multiplied by the change in the specific volume, that is 1.6930. So this comes out to be 2257.5 kilojoule per kg. Okay, so this is one way to find it. Another way is the direct use of HF and HG from the property table. So direct use of HF and HG at 100 kPa saturation pressure, HFG is HG minus HF. So this is 2675.0 minus 417.5. So this also comes out to be 2257.5. So we can say that both these values give both these ways give the same value. Now the amount of energy transferred to water, this is equal to mass multiplied by HFG. So this is 0.2 multiplied by 2257.5. This is basically 451.5 kilowatt. I hope it is clear to everybody. So let me go ahead with the next problem. A closed container of volume 0.5 meter cube is placed on a hot plate. Initially, the container contains a two-phase mixture of saturated liquid water and saturated vapor at pressure of 1 bar. At a pressure of 1 bar, and quality 0.5. After after heating, the pressure becomes 1.5 bar. Determine the temperature at the two states, the mass of vapor in the two states, and the pressure in the container at which only saturated vapor will be present if heating is continued. So what is the process here? The volume of the container is given to be 0.5 meter cube, and it is a rigid container. So at the stage 1 it is at 1 bar pressure and has a quality of 0.5. Okay, that is the vapor fraction, that is the mass fraction of the vapor at this at the first stage is 0.5. Then it is heated such that only such that at the stage 2 the pressure becomes 1.5 bar. We have to determine what is the mass of the vapor in the two states. Okay, and so essentially the quality at the stage 2 is not known. Now in the final part, if the heating is continued such that only vapor is present, that is the mass fraction of vapor becomes 1, that is the quality becomes 1, then what is the final pressure inside the container? So this is our problem in hand. So how will we go about it? So first we will state the property values at the salient points. So corresponding to the state 1, corresponding to 1 bar. So 1 bar is basically 0.1 MPa. So corresponding to 0.1 MPa, the values for corresponding to 0.1 MPa, this is the saturation temperature. This is the saturation temperature. 0.1 MPa. T saturation is 99.606 degrees Celsius, or so let me keep it in Celsius itself, and corresponding to 1.5 bar, that is 0.15 MPa. Okay, so this is 0.15 MPa. The saturation temperature is 111.349 degrees Celsius. Okay, so the since this is essentially the entire process is in the saturation region, I mean in the two-phase region. So at this point, at the stage 1, this 1 bar pressure will be essentially be the saturation pressure at stage 1, and at the stage 2 also this 1.5 bar pressure will also be the saturation pressure corresponding to that stage. Okay, so the corresponding values of the saturation temperatures will give the temperature at the two states. Okay, so the temperature of the stage 1 is state 1 is 99.606 degrees Celsius, and temperature of state 2 111.349 degrees Celsius. Okay, so now the second part of the problem, we will asked to determine what is the mass of the vapor in the two states. So correspondingly we will take help of the values of the specific volume at the two states. So in the state 1, this is the specific volume value of the liquid phase. Since it is a mixture, so it will be some multiple of this. There will be a factor x multiplied to the VFG value. So we have to take both these values from here, and these values as well, VF and VG values corresponding to 0.15 MPa saturation pressure or 1.5 bar. So at 1 bar Vf is equal to 0.00104315 meter cube per kg, and Vg is equal to 1.6939 meter cube per kg. Okay, in the stage 1 we know that the dryness fraction is 0.5. Okay, so what is the specific volume in the stage 1? This is Vf plus x into Vg minus Vf. This is x1 essentially. All these values correspond to state 1. So if we put in the values, we will get it to be 100104315 plus 0.5 multiplied by 1.6939 minus 0.00104315. Okay, so this value comes out to be 0.8475 meter cube per kg. We know that the volume of the container is 0.5 meter cube. Then what is the mass inside? This is the specific volume value, that is then V, this is constant by M. Okay, the volume of the container is rigid, and so the mass of the container, see, it is a closed container which is undergoing the process, so the mass and the volume will all remain same. Okay, so essentially in all these states, one point that we have to consider, that since the volume is constant and a fixed mass of the two-phase mixture of water and vapor is being heated, so the mass and the volume both remain same. So essentially the specific volume value will remain same in all the three states. Okay, anyway, so what is the mass here? The mass is volume by 0.8475, so it is basically the volume, this value is 0.5, so it comes out to be 0.589 kg. Okay, then the mass, the total mass inside the container is this. Therefore total mass inside the container is 0.589 kg, and therefore the mass of vapor inside the container at stage 1 is equal to this x1 multiplied by m. Let me denote it as m. This will be basically small m. Small m. So this is 0.5, so it comes out to be 0.295 kg. Again at the stage 2, that is 1.5 bar pressure, the Vf value is 0.00105273 meter cube per kg, and the Vg value is 1.1593 kg. So the point that I was telling before, that since the closed container is rigid, is rigid, the total volume remains constant. Fixed. And mass of mixture also remains constant. Therefore, the specific volume, that is the ratio of volume to mass, is constant. Okay, so basically V1 is equal to V2 is equal to V3. So therefore we have we can write V2 is V1 that we have found to be 0.8475, 0.8475. So this can be written as Vf plus x2 Vg minus Vf, these values corresponding to the state 2, 0.8475. So we know the values of Vf and Vg, so x2 putting those values, x2 comes out to be equal to 0.7308. Therefore the mass of vapor in this at this time, therefore mass of vapor in state 2 is equal to x2 into m, that is 0.7308 multiplied by the total mass, that is 0.589, so it comes out to be equal to 0.4304 kg. So we can see that due to heat, more vapor is produced, that is the mass of vapor has increased from 0.295 kg to 0.4304 kg. Okay, so now the last part of the problem, we have been asked to find the pressure in the container only if only saturated vapor is present, that is if the heating is continued, now the entire liquid will be converted to vapor. That is in that stage, when the dryness fraction becomes equal to 1, what is the final pressure? In this state also the specific volume will remain the same. Okay, so is you see here x3, when only saturated vapor is present, then x3 is equal to 1 and v3 is equal to v1. So this is basically 0.8475 meter cube per kg. So since it is saturated vapor, so this v3 value will actually be you can write it as vf plus 1 into vg minus vf is equal to 0.8475, or that will ultimately it will be the value of the saturated vapor phase. Vg is 0.8475. Okay. So from the table we have to find the saturation pressure corresponding to this value of the specific volume of the gas phase. So we can see that 0.8475 lies between these two values, 0.84614 and 0.88568. So if we perform an interpolation, we will get the value, the corresponding pressure value between these two. Okay, so let us perform the interpolation. By interpolation, 0.8475 minus 0.84614 by 0.88568 minus 0.84614. The easiest way is to write the pressures corresponding to these values. So 0.8475, we have to find this value, minus for 8.84614, it is 0.21. This is, and this is 0.20 minus 0.21. Okay, so P3, let me denote it as pressure at the state 3. So P3 equals to 0.21 minus, this is 0. Minus 0.01, so minus 0.01 multiplied by this value, comes out to be 0.0344. So this is 0.2096 MPa or 2.096 bar. Okay, therefore pressure, final pressure in container when only saturated vapor is present, is this value, 2.096 bar. So we can say that due to heating, finally the pressure will increase from 1 bar to first to 1.5 bar and then to 2.096 bar. Okay, when the entire water has converted to vapor. So I hope this is clear to everybody. If there is any doubt, you can ask. Okay, so let's move on to the next problem. A pressure cooker, which is a closed tank again, contains water at 100 degrees Celsius with the liquid volume being 1/20th of the vapor volume. Okay, so it is heated until the pressure reaches 2 megapascal. Thus the final stage has more or less vapor than the initial stage. So what happens is that a pressure cooker, it contains a fixed quantity of water, where the liquid fraction, it contains a mixture of water and vapor, where the liquid volume being, where the volume of the liquid is 1/20th of the vapor volume. Okay. Now this mixture, it is heated until the pressure reaches 2 megapascal. So thus the final stage has more or less vapor. So initial state, this is 100 degrees Celsius. This is water plus vapor mixture, and the volume of the liquid phase here is 1/28 of the volume of the gas phase. Okay. And this is the total volume. It is the total volume. Now at 100 degrees Celsius, but this is not essentially, this is not this is not the ratio or anyway giving a value of the dryness fraction, because the dryness fraction is related to the mass, not the volume. So for we have to use this data to find the dryness fraction first. At 100 degrees Celsius, the specific volume of the liquid phase is 0.00104346. at 100 degrees Celsius, this value, and the Vg value is 1.6718. Okay, now VL is 1 by 20 of Vg. So VL can be written as the mass of the liquid phase multiplied by specific volume of the liquid phase, right? This is equal to 1 by 20 of mass of the gas phase multiplied by specific volume of the gas phase. So the mass of the mass of the gas phase to the mass of the liquid phase is equal to 20 times Vf by Vg. So this value comes out to be 1 by 80.11. This is also not a dryness fraction, because dryness fraction is the ratio of the mass of the vapor to the total mass of the mixture present. So from mg by ml we do this one, mg by ml plus mg is equal to 1 by 80.11 plus 1, that is 1 by 81.11. So this value, that is mg by total mass, which essentially comes out to be 0.0123, this will be the dryness fraction of the state 1, x1. Now since the container is rigid and the mass is fixed, so this specific volume value will also be the same in all the states, okay, during the heating process. So in the final state, the specific rigid container plus fixed mass will imply the specific volume is constant. Okay, now for the final state, where it is in 2 megapascal pressure, okay, this is also a mixture of water plus vapor. So V2 is equal to V1 is V2 is V2, this is equal to V1, okay, and what was V1? V1 is equal to Vf1 plus x1 into Vg1 minus Vf1. So if we put in these values, the V2 value comes out to be equal to 0.02159 meter cube per kg. Okay, and but the V2 value, we can write it as Vf2 plus x2 Vg2 minus Vf2, 0.02159. So corresponding to 2 megapascal, and the Vf value is this and Vg value is this. So if we put in these values, we will get the value of x2 to be 0.2074. Okay, so initially the fraction the dryness fraction was 0.0123, now it is 0.2074. So the volume of vapor has increased. Therefore I mean, we can write it, since x2 is greater than x1, so the final stage has more vapor than initial stage. I hope it is clear to everybody. If there is any doubt, you can ask, else I will move on to the next problem. Okay, let me start with the next problem. So saturated, that is liquid plus vapor water at 30 degrees Celsius is contained in a rigid steel tank of volume 0.2 meter cube. It is used in an experiment where it should pass through a critical point when the system is heated. The mass of water, that is liquid plus vapor inside the tank, is what? That is the total mass of the mixture inside the tank. So corresponding to 30 degrees Celsius, what happens is, let me start with the explanation of the critical point here. So what is the critical point? If we plot this diagram, then we can see that it will move like this, like mm, yes. So like this it moves. Constant temperature lines will be like this. So above this point, okay, above this point there will be no this mixing zone, that is the saturation zone or the liquid plus vapor zone or the mixture zone will not be present above this. The at this temperature, from this pressure value onwards, at any temperature the mm, uh, liquid will directly convert to vapor phase like this. So this is the critical point above which there is no boiling or there is no phase change seen. So this is the critical point. Okay, so the critical point for this is the critical point. Now at the critical point, corresponding to the critical point of water, there is a particular critical specific volume corresponding to this value. Okay, so the critical volume for water, critical volume for water is, this is basically critical specific volume for water is 0.00310056 meter cube per kg. Okay, now what is being said here? Okay, so it is somewhere here. Okay, it is somewhere here, and during the heating process it should pass through the critical point. So during this heating process the process should go like this, that is it should pass through the critical point. Okay, so it should pass through this critical point. Since it is a rigid container and it contains a fixed mass of water, so the specific volume will remain same again. So the specific volume at the state 2 will be equal to the specific volume at the state 1, which is and the specific volume at the state 2 is basically the critical specific volume. Therefore the specific volume in the state 1 is equal to 0.00310056, okay, meter cube per kg. Now this is the specific volume and this is the total volume. So the total mass of water inside the tank is mass of water is m, that is v by specific volume. V, this is 0.2 by 0.0031056. So this value comes out to be 64.4 kg. So this is the option A. Okay, this one. Now, a similar type of question, a sealed rigid tank contains 1 kg of water at 200 degrees Celsius with a volume of 0.005 meter cube. Okay, the tank is now heated. What happens to the liquid level inside the tank? Okay, so it is basically a container, rigid container. It contains some water plus vapor mixture. Now it is being heated. So will the liquid level may increase? I mean, how, when will the liquid level increase? If the if vapor is being converted to liquid. When will the liquid level drop to the bottom of the tank? When the liquid is being converted to vapor, and the liquid level will eventually rise to the top of the tank, that is the vapor will finally get converted to entire liquid, and the last option is it cannot be determined. So how will we try to do that? So the mass of the container is 1 kg, the volume is 0.005, so the specific volume in the state 1 is 0.005 meter cube per kg. Okay, since the specific volume will remain the same for a rigid plus fixed mass, implies V2 is equal to V1. So V1 is 0.005 meter cube per kg. Okay. So at state 2, the specific volume is 0.005 meter cube. We cannot essentially write it at this point. It could have been well enough that the point 1 was somewhere here and it would have gone like this. Okay, or it could have passed directly like this. So this V2, now this V2 value, it is greater than the critical specific volume, which is equal to, we have already used this 0.0031056, 0.0031056. Okay, so since it is higher than this one, so it will lie on this side. So this phase implies that as it crosses the point 2, the entire liquid will now, this is a complete vapor region, right? This is a complete vapor region. So this as it gets heated and it crosses the point 2, it will get completely converted to vapor, that is the entire liquid will get converted to vapor. So the liquid level will eventually drop to the bottom of the tank. Okay. Therefore liquid in this case, liquid completely evaporates. Therefore liquid level drops to the bottom of the tank. Okay, so B. I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so I'm taking that there is no doubt. then I will move on to the next problem, which is essentially a modification of this previous problem. So now in this question, sorry, this will be not question number 3, it is question number 5. So in the question number 5, if the mass is 2 kg instead of 1 kg, what will be the change in the result? So in this case, the specific volume in the state 1 is 0.005 by 2. So this is 0.0025 meter cube per kg. Okay, so this is less than the critical specific volume. Okay, so what happens is that in this case, as we heat it, this point 2 will lie to the left of the critical volume, and this is a completely liquid region. Okay, so this will get converted to the complete liquid. Okay, so therefore all the mixture, all the vapor here gets converted to liquid. Therefore, the liquid level will eventually rise to the top of the tank. So, a very interesting fact to note here is that just depending on the total mass, it will determine what will be the final effect of the heat addition be. We cannot just generally say that there is a mixture of water and vapor, so if we heat it, only water will be converted to vapor, that is, more vapor will be produced. This is not the case. Okay, it will depend on the conditions in which the process is happening. In this case, it is a constant volume process. Okay, that is the constant volume process, so that is a constant specific volume process. So depending on the mass that is initially present, and the final specific volume value relative to the critical specific volume, we will see that either the entire liquid will be converted to vapor, or the entire vapor will be converted to liquid, which might appear as opposite to our intuition. However, in this case, so where is this heat addition going? So this heat addition is appearing as the increase in the pressure of the liquid. Okay, so at this point the pressure of the liquid was something less, so in this point the pressure of the liquid will be something significantly higher. So it is like, you can say that due to heat, the pressure of the mixture is increasing, and this pressure is this pressure is compressing back the vapor fraction of the mixture to the liquid phase. Hence the vapor gets converted to the liquid, even though heat is being added. So the liquid level will eventually rise to the top of the tank. So I hope it is clear to everybody. uh, if yes, then I will move on to the next problem. Okay, so let us begin with the let us start with the next problem. A piston cylinder assembly contains saturated water, that is liquid plus vapor, at 75 degrees Celsius, that is state 1. Initially the piston movement is arrested, that is the piston is not free to move, using a pin, and the water is heated till 150 degrees Celsius. So during this heating process the volume remains constant since the piston cannot move. Okay, so this is a constant from 1 to 2. This is a constant volume process. Okay. At the state 2, it states that the liquid just disappears, that is it is a saturated vapor phase. Now the pin is removed and the water is heated at a constant pressure. So after this state, when it reaches saturated vapor phase, the pins are removed and the piston is now free to expand. So there will be a constant pressure heating process till 300 degrees Celsius is reached, that is the state 3. Okay, so in a constant pressure process it reaches state 3. So we have to determine what is the initial quality of this mixture. So it is a mixture, right, of liquid plus vapor. So what is the initial quality and the final specific volume of the water vapor. Okay. So let me write the process first. So it is a from state 1. Okay, it is at 75 degrees Celsius and constant volume heating. Heating, it will reach the stage 2, which is 150 degrees Celsius, such that the liquid just disappears. Okay, now there is this constant pressure heating to stage 3 at 300 degrees Celsius, which is a superheated vapor now. Okay, now from the steam table, at 75 degrees Celsius, the saturation pressure is 0.032575 MPa. VF1 is 0.0010258 meter cube per kg, and VG1 is 4.1289 meter cube per kg. And at stage 2, that is 150 degrees Celsius, the saturation pressure is 0.47616 MPa, and this is like P2, and VG2 is V2 0.39245 meter cube per kg. Why? Because at a stage 2 it is saturated vapor. For rigid plus fixed mass system, the specific volume remains same. Therefore, V1 is V2 0.39245 meter cube per kg. Okay. Therefore, we can write Vf1 plus x1 into Vg1 minus Vf1 is 0.39245. So putting these values, we get x1 to be 0.0948. 0.0948. Okay, so this is a dryness fraction. For initial quality of therefore the initial quality of mixture that is in the initial stage 0.0948 is the mass fraction of vapor in the mixture. Okay, now they state the process 223 is a constant pressure heating process such that this pressure P2 is equal to P3 is equal to 0.47616 MPa. Now corresponding in the saturation stage 3, at a stage 3 this is not a saturation temperature anymore. At a stage 3 the temperature is 300 degrees Celsius. So this is essentially, these two will give a superheated vapor. So corresponding to the from the steam table corresponding to from the steam table corresponding to a temperature of 300 degrees Celsius, and so in from the superheated table corresponding to 300 degrees Celsius. Okay, this is common, and 0.45 MPa. At this pressure, the specific volume is 0.5814 meter cube per kg, and at 0.5 and at 0.5 MPa the specific volume value is 0.52261. Okay, therefore we have to do an interpolation between these two pressure values to get the pressure specific volume corresponding to this pressure value P3. Okay, so if we do an interpolation, we'll get V3 is 0.58140 plus 0.52261 minus 0.58140. 658,140 divided by 0.5 minus 0.45 multiplied by 0.47616 minus 0.45. So these are the pressure values and these are the specific volume values. So this gives the specific volume value to be 0.5506 0.5506 meter cube per kg. Okay, so the final specific volume of the water vapor, therefore final specific volume of water vapor is 0.5506 meter cube per kg. This is the answer to question B. So I hope it is clear to everybody. If there is any doubt, you can ask, else we will move on to the next problem. Okay, so I am taking that there is no such doubt. So we will move on to the next problem. So this is an application of the ideal gas equation and the compressibility chart. So taking refrigerant R134A as a pure substance, we have to determine certain values with respect using the ideal gas equation and then using the general compressibility chart. So what is basically the compressibility? So for an ideal gas, we follow the equation for ideal gas. It is basically for ideal gas use P V is equal to M R T. Okay, or P specific volume is equal to R T. So how do we define this compressibility? We define this compressibility Z as the ratio of PV is equal to RT, PV by RT. For ideal gas, Z is equal to 1 since PV is equal to RT. For real gases, Z is not equal to 1. So there is a variation. How do we get this basically? So if there is a piston cylinder device in which there is a fixed mass of any particular gas, which is so as it is uh, being heated, if a piston cylinder arrangement containing a fixed mass of gas, any particular gas, when it is being heated, such that we maintain the process in such a way that it is an isothermal process. Okay, so with the increase, with the change in the pressure, there will be a change in the volume. Okay, so at any particular temperature, okay, if we plot the value of PV by T with respect to the pressure, okay, so by changing as it is being heated, uh, the expansion process, throughout the expansion process there will be different values of pressure and the specific volume, right? um, Keeping the temperature constant. So this PV by this temperature value, this ratio, uh, when plotted against the pressure value for any particular temperature T, okay, it will follow a profile like this. So at different values of temperature, if we repeat this process by keeping the different values of temperature constant, if we repeat this process, we will see that the graphs are coming like this. Okay, and if we extrapolate it to zero pressure value, okay, we will get a fixed point. Okay, let us say this is R. So that is at uh, mm, this PV by T value becomes equals to R when the pressure tends to 0. When we repeat this process for all many other gases, then we will find that this R value for all these processes, for all these gases, come to be constant. So this R value is called a universal gas constant. Okay, that is 8.314 kilojoule per kilomole Kelvin. Okay, so this is how we get it. This is a universal gas constant. So we can write that limit of pressure tends to 0, PV by RT, this is equal to or PV by T basically tends to R, or limit of pressure tends to 0, PV by RT, this value is Z, right? This is equal to 1. So as pressure tends to 0, Z tends to 1. Sorry, Z tends to 1. From this we can say that the real gases under very low pressures will tend to behave as an ideal gas. Okay, so and in that circumstances it will follow the ideal gas equation. In all other cases, Z is not equal to 1. That is, this ratio PV is not equal to RT. Okay. Now, when we in the previous problems, when we have used this critical point value, so at the critical point value, there will be critical pressure, critical temperature, and critical specific volume. Okay, so corresponding to this, we define one ratio as reduced pressure and reduced temperature, PR and TR, that is reduced pressure and reduced temperature, reduced pressure, PR, this is equal to any value of pressure by the critical pressure, and reduced temperature is TR is T by T critical. So based on the values of PR and TR, for many general gases, it is found that uh, all of these gases almost follow the same trend in the variation of this compressibility Z with respect to PR and TR. So we get a compressibility chart, that is the which is a which is like this. I mean, this is so PR, PR, and this is corresponding to sorry, this is Z value. Okay, and this is the reduced pressure value. So, these graphs are drawn for different values of uh, like these graphs are drawn for different values of TR, different values of TR. Okay, so for any particular state we'll get the TR value, so we will get the value on this graph, and for any PR value we will from these two values we'll get the corresponding value of Z, that is the compressibility factor. Okay, so that is the use of the generalized compressibility chart. Why generalized? Because most of the common gases follow this I mean have the similar variation of the compressibility based on the reduced pressure and temperature. So how can we use this? Uh, now, first, using the ideal gas, given pressure is 1 megapascal, that is 10 to the power 6 pascal, temperature is 50 degrees Celsius or 323 Kelvin. So the molecular mass of R134A, this is tetrafluoroethane, right? So this is basically C2H2F4. So the molecular mass is 102, and this gives the R value to be 8.314 by 102, that is 0.0815 kilojoule per kg Kelvin. So from the ideal gas equation, okay, PV is equal to RT. So uh, this is will be the universal gas constant. Let me do it as a R bar. Okay, and this is RT. So uh, the specific volume is RT by P. This is 0.0815 into 10 to the power 3 to 323, and divided by pressure is 10 to the power 6, so it gives the value of 0.026325 meter cube per kg. Okay, so what is the percentage error here? Percentage error with respect to the actual value of 0.021796, percentage error is 0.026325 minus 0.021796 by 0.021796. This is equal to 20.78%. Now using the compressibility chart, okay, so for R134A, the critical pressure is 4.059 MPa, 4.059 MPa. This implies the reduced pressure becomes 1 by 4.059, that is 0.246 MPa, and the critical temperature is 374.2 Kelvin. So the reduced temperature becomes 323 by 374.2, that is 0.863. So corresponding to these values from the generalized compressibility chart, we will get the value of Z to be nearly equal to 0.84. So this generalized compressibility chart can be found in any of the standard textbooks, and mostly in the appendix part, where they have given this chart as an uh, addition additional resource for the use of the students. So the final specific volume is Z multiplied by the ideal the specific volume using the ideal gas equation. So this comes out to be 0.84 multiplied by 0.026325, that is 0.022213 meter cube per kg. Okay, so what is the percentage error here? 0.022213 minus 0.021796 by 0.021796, that value comes out to be equal to 1.45%. So you can see that by the use of this compressibility chart, the percentage error has decreased from nearly 21% to 1.5%. So it is a significant decrease in the error just by the use of this compressibility chart. So I hope it is clear to everybody. If there is any doubt in this, please let me know. Okay, so let me move on to the next problem. To predict the pressure of nitrogen gas, which is again a pure substance, at temperature of 175 Kelvin and specific volume of 0.00375 meter cube per kg on the basis of the ideal gas equation of state and the van der Waals equation of state. Compare the values obtained to the experimentally determined value of 10,000 kilopascal. So, what is the van der Waals equation? So, one way of predicting of realizing the behavior of the gases is the use of the compressibility chart. Another use is the modification of this equation. This equation has been modified by many many times by many scientists, and one of them is van der Waals, who gave the modified equation as P plus A by V square, V minus B is equal to RT. So what are A and B? This is the van der Waals equation. Equation of state. So what are A and B? So consider a um, uh, particular gas in a container. These molecules of the gas will have an intermolecular force of attraction between them. So this intermolecular force of attraction between them will contribute to a pressure value. That contribution comes with the addition of this A. So this A basically takes care of the intermolecular forces of attraction. Now this volume, this volume, we have taken the entire volume of the container. However, uh, 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 the gas molecules, however small their volume might be, but each of these gas molecules will occupy some volume. So this entire volume of the container will not be available as the actual volume. This B will take care of the volume of the molecules. Okay, so this B basically takes care of the volume of the molecules, and this A takes care of the intermolecular forces of attraction. So this is the van der Waals equation of state, which is just a modification of this ideal gas equation. So how will we determine the values of A and B? For this we will use two equations. So as we have seen, at this critical point the slope becomes like this, right? The slope becomes like this. So the slope becomes essentially 0 at the critical point. So at critical point dou P by dou V at constant, at this temperature is a critical temperature, T is equal to T critical, this is a constant temperature is 0, and also del 2 dou P by dou V and dou 2P by dou V 2 at constant temperature, that is a critical temperature, is also 0. The first derivative and second derivatives are both 0. So from this P plus A by V square is V minus B is equal to RT. From this we get P equals RT by V minus B minus A by V square. Therefore now we write del P by del V at T equals to T critical, P equals to P critical, and V equals to V critical, and that is we write this value at the critical point. So first we differentiate it, it comes out to be RT. This differentiation will give 1 by V minus B whole square minus 1 upon V minus B whole square minus twice A by V cube. This is 0. Since it is at a critical point, so this will be EC, this is VC, and this is also VC. So we can write A to be equal to RTC VC cube by VC minus B whole square. This is equation 1. Now we use the second derivative. What is this one? Differentiation of this again. So RT minus of this one minus of 1 upon V minus B whole square, derivation of this will give sorry, not derivation, pardon, it is so the differentiation of um, 1 upon Vc minus B whole square with respect to 1 upon V minus B whole square with respect to V, it gives the value minus 2 by V minus B whole cube. Okay, and in this it is minus 2a this will not be minus, this will be plus. This is already minus and this is also minus, so it will be plus. This is plus, if I say, by minus 3 by v to the power 4. Therefore, del 2p by del v2 at t equals to tc, p equals to pc, and v equals to vc is equal to 2rtc by vc minus b whole cube minus 6a by vc to the power 4 equals to 0. This will give the value of a to be rtc vc to the power 4 by thrice of vc minus b whole cube. This is equation number 2. Now from 1 and 2, from 1 and 2, we RTC VC cube VC minus B whole square. This is equal to RTC VC to the power 4 by 3 VC minus B whole cube. This gives VC is equal to price of VC minus B plus, there is a 2 here. This will give the value of B equals to VC by 3, or VC is equal to 3. Now 1, therefore if we put this value in 1, we get A equals to RTC VC cube by twice of VC minus B. RTC VC cube, this VC can be written as 3B, so this will be 27B cube, and this is 2 multiplied by VC minus B is 2B, so VC minus B whole square, so this is 2B whole square, so 27 RTC by 4B, but B is VC by 3, so this is 27 RTC VC by, if we put VC by 3, then it will come out 9. 9, this is 8, 9, 8. 9 by 8 RTC VC. Okay, so we have PC is equal to RTC by VC minus B minus A by VC square. specific volume. 0.2968 into 10 to the power kilojoule, so it will give in kilopascal if we keep it in kilojoule itself, and multiplied by the temperature is 175 by 0.00375, so it gives the value of 13851 kPa. Okay.
Battery is fully charged.
Now percentage error with respect to experimental actual pressure is 13851 minus 10,000 by 10,000 into 100%. It gives us 38.5%. So there is significant error in the value of pressure using the ideal gas equation. Now using the generalized compressibility chart. Now for nitrogen, the critical pressure is 3390 kPa and the critical temperature is 126 Kelvin. Therefore, A is 27 R square Tc square by 64 Pc. So putting in this value 0.2968 whole square multiplied by critical temperature whole square by 64 multiplied by critical pressure is 3390. So this is 0.2968 in kilojoule, right? So 10 square will be 10 to the power 6 and 3390 is in kilopascal, so 10 to the power 3. It gives the value of 0.174 meter cube meter to the power 6 kilopascal per kg square and B is Vc by 3 or 8 RTC by 8 Pc. So this is 0.2968 into 10 to the power 3 into 126 by 8 into 3390 into 10 to the power 3. So it gives a value of 0.00138 meter cube per kg. Okay. Now using the van der Waals equation, P is equal to RT by V minus B minus A by V square. So A, B and all these values are known. So 0.2968 multiplied by 175 by what is the specific volume, 0.00375 minus 0.00138 minus A is 0.174. This is V squared 0.00375 whole square. This is 21915.61 and this comes out to be 12373.33. Net value comes out to 9542.28. 42.28 kPa. Therefore, percentage error with respect to experimental value is 10,000 minus 9542.28 by 10,000 into 100%. So this gives the value of 4.5%. Okay, so you can see that the percentage error has decreased from around 40% to 4.5%. This is like almost a 8 to 10 9 8 to 10 times uh, decrease in the percentage error. So using the Van der Waals equation, a significant improvement in the result can be achieved. Okay. So I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so I am moving on to the next problem. This is the application of this concept to the I mean, this is basically a problem related to the working of a refrigeration cycle. There's a vapor compression refrigeration cycle in which the refrigerant is considered as a pure substance. So the refrigerant R134A is being used as a working fluid in a refrigerator which operates on an ideal vapor compression refrigeration cycle between 0.14 and 0.8 megapascal. So this is 0.14 megapascal and this is 0.8 megapascal. Now if the mass flow rate of the refrigerant is 0.05 kg per second, determine the rate of heat removal from the refrigerator space and the power input to the compressor, the rate of heat rejection to the environment, and the COP of the refrigerator. So this refrigeration cycle, let us start from the point 1. So from the point 1, if it is an ideal vapor compression refrigeration cycle, then it will be a saturated vapor state. So from this point to the point 2, there will be a isentropic compression of the refrigerant using in the compressor, thus requiring the compressor input work. So this is basically the compressor input work which results in the compression of the refrigerant from the state point 1 to the state point 2 isentropically. Now at the state point 2, this compressed refrigerant will lose heat to the environment in the condenser. This occurs at a here it occurs at a higher pressure of 0.8 megapascal, releasing heat to the ambient. So there is heat loss to the ambient during this process. Now from 3 to 4, there is a throttling process, as we have discussed in the previous classes, that the expansion process or the throttling process 3 to 4, that is a throttling process essentially here. 3 to 4 is a constant enthalpy process which we have derived from the which we did derive from the energy equation. So the enthalpy remains constant from state 3 to state 4. Now at the state 4, it enters the evaporator, which actually removes the heat from the cooling space, that is the space which is being cooled. So from 4 to 1, it accepts, it takes in heat from the space that is being cooled, that is it takes in the cooling load which is denoted as Q in, resulting in the conversion of this mixture. It is a mixture of liquid and vapor, right? So there is a conversion due to this absorption of it. There will be a conversion of this mixture to a completely to a saturated vapor phase. So thus completing this cycle. This process here occurs at 0.14 megapascal. Now we have to determine what is the compressor work input, what is the heat rejected to the ambient, what is the heat that is being taken from the refrigerated space, and what is the COP of this cycle or the refrigerator. Okay. Now for R134A, corresponding to 0.14 MPa, H1 is equal to Hg at 0.14 MPa saturation pressure. So this value is 239.1 239.16 kilojoule per kg, and the entropy at the state point 1 is entropy of the vapor phase at 0.14 saturation pressure, that is 0.94456 kilojoule per kg. Now, since it is an ideal vapor compression refrigeration cycle, so the process 1 to 2 is isentropic. For ideal vapor compression refrigeration cycle, the compression is isentropic. That is S2 is S1 is 0.94456. Now corresponding to this pressure, corresponding to a pressure of 0.8 MPa, which is a condenser pressure, and S2 is equal to 0.94456 kilojoule per kg, we get the enthalpy value to be 275.39 kilojoule per kg. This is obtained from the superheated data table of refrigerant R134A. Now, for ideal vapor compression refrigeration system, this exit point of the condenser will be saturated liquid. So, H3 will be HF at 0.8 MPa. This is equal to 95.47 kilojoule per kg, and for throttling, H4 is equal to H3, the throttling process, it is equal to 95.47 kilojoule per kg. Now we have the enthalpy values at all the salient points. Now we have to just find out the values. Here's a rate of heat removal from refrigerated space. This is Q in. This is m dot H1 minus H4. H1 minus H4. This is the region where the heat is being removed from the refrigerated space. So this is mass is 0.05 kg per second, 0.05 kg per second. Enthalpy difference is 239.16 minus 95.47 This value comes out to be 7.18 kilowatt. The power input to compressor WC is m dot h2 minus h1. This is 0.05 to 75.39 minus 239.16 minus 239.16. So this comes out to be 1.81 kilowatt. The rate of heat rejection to the environment Q out is m dot h3 minus h2. Sorry, h2 minus h3. From h2 to h3 is the heat rejection in a condenser. This is again 0.05. h2 is 275.39 minus 95.47. It gives a value of minus 8.99. Sorry, this will be h3 minus h2 only, so it will give a negative value in that case. h3 minus h2, 95.47 minus 275.39. This is minus 8.99 kilowatt. Okay, and the COP of the refrigeration system is Q input by WC, that is 7.18 by 1.81, so this is 3.97. Okay, okay, so I hope it is clear to everybody. Then we'll move on to the next problem, which is essentially a modification of this problem. So in the previous problem we have used a ideal vapor compression refrigeration cycle. Now we are using an actual vapor compression refrigeration cycle. So actually what happens, as the refrigerant moves through the evaporator will be like in some form of a pipe, okay, or as it flows through the pipe, there will be frictional losses. So due to this frictional losses, earlier we took that the entire evaporation and the condensation process occurs at a constant pressure. However, in this case, those will not remain the same. So what is the problem at hand here? The refrigerant enters the compressor of a refrigerator as a superheated vapor, okay, at 0.14 MPa and 10 degrees Celsius at a rate of 0.05 kg per second, and leaves at 0.8 MPa and 50 degrees Celsius. So the refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 MPa and is throttled to 0.15 MPa. Disregarding any heat transfer and pressure drops in the connecting lines between the components. Between the components, there is no pressure drop. Determine the rate of heat removal from the refrigerated space and the power input to the compressor, the isentropic efficiency of the compressor, and the coefficient of performance of the refrigerator. So it is stated that we have to neglect the pressure drop in the connecting components. So like this is the evaporator and this is the compressor. So at this point there will be no other pressure drop. At this point there will be no other pressure drop. At this point there will be no other pressure drop, and at this point there will be no other pressure drop. However, in between the in a particular component itself, there will be a pressure drop. So in the evaporator, you can see that after the throttling process, it is throttled to 0.15 MPa. but during the flow of the refrigerant in the evaporator tube or in the evaporator tube, due to the frictional losses there will be pressure loss. So in the pressure, and the pressure loss is 0.01 MPa. So 0.01 MPa, that is like 10 kilopascal pressure is lost due to the movement of the fluid in the evaporator tube. So the exit of the at the exit of the evaporator, the pressure is 0.14 MPa and minus 10 degrees Celsius. It is then compressed to 0.8 MPa and 50 degrees Celsius. It is not essentially an isentropic compression. This is an actual cycle and it is not a reversible one. So even if it is adiabatic, it won't be isentropic. So in this case, due to this, since the process is not isentropic, so there will be an increase in the entropy of the entropy at the exit point, because the entropy generation term in this case will be greater than 0. So the entropy at the state point 2 will be greater than entropy at state point 1. Okay, and this point is the point corresponding to the isentropic compression. Now from 0.8 megapascal, as the refrigerant is flowing through the condenser tube, it again undergoes a pressure drop, and the pressure drop is more here, like it is 0.08 MPa, that is 80 kilopascal here. Okay, in the condenser. And uh, so since it is not a uh, constant pressure process, so if it had been a constant pressure process, it would have been somewhere here, I mean on this slide. However, because of the pressure drop, it has come to here. Okay, that is 0.8 MPa, from 0.8 MPa to 0.72 MPa. Now then the remaining is a throttling process. Okay, so for this process, we let us write the salient points here, like 1 to 2s, which is the isentropic compression. Isentropic compression. 1 to 2 is the actual compression. Okay, from 2 to 3 there is pressure drop in the condenser from 0.8 to 0.72 MPa, and from 4 to 1 there is pressure drop in the evaporator from 0.15 to 0.14 MPa. Okay, now let us try to find out the properties at the salient points. So at the state point 1 is 0.14 MPa and minus 10 degrees Celsius, which is a superheated region, vapor region. The enthalpy value is 246.36 kilojoule per kg. At state point 2, which is 0.8 MPa and 50 degrees Celsius, the enthalpy is 286.69 kilojoule per kg, and the entropy at a state point 2 is not equal to the entropy at state point 1 because it is not an isentropic process. The state point 2, 3, that is 0.72 MPa and 26 degrees Celsius, the enthalpy at a state point 3 will be enthalpy at the of the saturated liquid corresponding to 26 degrees Celsius, because since the pressure lines are very close to the saturation curve in this region, so the pressure the point 3, even if it is a bit away from the saturation curve, we consider it to be the equal to the enthalpy of the liquid phase lying on the saturation curve corresponding to this temperature of 26 degrees Celsius. So this is equal to 87.83 kilojoule per kg. And 4, this is a throttling process. So H4 is equal to H3 is equal to 87.83 kilojoule per kg. Okay, so the rate of heat removal from the compressor from the refrigerated space is m dot h1 minus h4. So this is 0.05 246.36 minus 87.83. This is 7.93 kilowatt. Okay, and the power input to compressor WC, this is Q in, this is m dot h2 minus h1 0.05 286.69 minus 246.36, that is 2.02 kilowatt. Now we have to find the isentropic efficiency. Now S2S, that is for the point corresponding to the isentropic compression, will have the same entropy as the state point 1. So S1, that is at 0.14 MPa and minus 10 degrees Celsius, the entropy value is 0.9724 kilojoule per kg Kelvin. Therefore, corresponding to 0.8 MPa and S2 is equal to 0.9724 kilojoule per kg Kelvin. H2S is 284.21 kilojoule per kg. Therefore, isentropic efficiency is isentropic work input by actual work input, that is m dot h2s minus h1 by m dot h2 minus h1. So if we put in these values, we'll get the isentropic efficiency to be 0.939, that is 93.90%. Okay, and the COP of the refrigerator is COP is Q input by WC is 7.93 by 2.02 3.93. Okay, so you see, as we move from the ideal vapor compression refrigeration system to the actual vapor compression refrigeration system, where the losses are involved, the COP decreases from 3.97 to 3.93. So this decrease in the COP is due to the losses in the components of the system. So I hope it is clear to everybody, and if yes, then we will end today's session. So let us end today's session.